Hi, I'm Tom and I talk about code. Welcome to another Rust programming live stream working on my compiler for a C-like language that runs on my own 16-bit virtual machine. Today we're coming back in. We started strings a couple of streams ago. We got sidetracked designing an entire binary format for my compiler to target. This was kind of a necessary step because of how strings relate to static data. Today we're going to circle back. We've got all the parsers and everything. We're going to finish off strings. Then we're going to do a bit of testing with strings, and to do this nicely, we're probably going to have some kind of API for defining constants, things that exist outside of the scope of the compiler. So things like memory addresses that mean something to the virtual machine specifically, so that our code can reference things, without having to make assumptions about the environment it's running in. And then once we can do that, we're going to build our language targeting WASM, and I'm going to hopefully integrate it into my web front end, so you can write this language in the browser, compile it, run it, step through programs line by line. It'll all be really good. So let's do it. Also, is today the 10th of August? Yeah, sure, today is the 10th of August. Infinite Coder, good morning, welcome. Well, hello. I don't know if it's morning or like what time it is for you, but you've got a really cool emote. I like this emote. This is a high quality emote. So thank you, and thank you for the shout out the other day. I can't remember if I said that already. Let's jump over and write some code. This is my test program. This is my string test program. Okay. We have a string. It is gonna get compiled. It's gonna get placed at some point in memory where we can reference it. Now, there's a couple of problems with how we currently do it, but I'm not 100% sure what they are, so I think it might be interesting to just run this program and see what happens. So if I cargo bin run my compiler on this file, what happens? It actually compiles, and that's interesting. Let's have a look at the binary. So, interestingly, the string seems to live down here. I don't know why the string lives down here. Oh no, actually I do. Because if we look at our compiler, I did a bunch of work off camera. I think I forgot to mention that. But if we look at how our compiler outputs code, it puts our code data first, then our static data second. So actually that makes sense. We have our string. Our string, foobar, is going to come along with a length, F-O-O space B-A-R. F-O-O. So this is the length of the string, and I guess this is a 16-bit number, so I guess that takes up two things. And that's fine. We want strings longer than 256, so that's good. And then we have the actual string itself, which is only 7 characters, 1, 2, 3, 4, 5, 6, 7, and then it stops. In this case, it's null terminated because it finishes on an odd byte, and we're going to pad that out 1 byte, but ultimately strings do not need to be null terminated because we pass the length along with it. So this whole block is a piece of static data known as a string. And if we have a look at our test program, we've defined a string type that has a length and some character data. Now, actually, this isn't quite right either, because what it should be, well, what we really want is this isn't a pointer to character data. This is character data. Well, I guess it can be. But when we load this as a reference, we can't just use this directly, because this points to a len and then a list of things, blah, blah, blah. There's a lot of complicated stuff. We need to work out exactly how we handle these strings. Exactly what we're doing here. So, I probably don't actually want this struct definition. That doesn't really make sense anymore. What we have is a string type. Let's say type string. Let's just say it's an alias to a generic pointer that has no real data, or maybe even a car pointer. That's okay. And we want a function. We'll make it an int. We'll say get string get. We'll call it strlen. We're gonna take a pointer to a string. No, we'll just take a string s. We're giving back an int, which is the length. Now we're going to have to do some casting. My language doesn't really support casting, so I need to think about how this is going to work. Good 8:36 p.m. Yeah, thank you. That's very accurate, that's very precise. However, there is a little bit of ambiguity in this date because you have opted for day, month, year. You know, if you want this to really be a very unambiguous greeting, it needs to be probably a full ISO timestamp, right? Year, month, day, hour, minute, second. That is my only feedback for you there, Cricket. Have you played any Doom yet, Cricket? So the length is, it's the first, we basically want to say let the pointer to the length, it's going to be s, but it's going to be s converted to an int pointer, right? And then we want to dereference that. Return s. Okay? I think that's good. The lack of inline struct initialization is hurting me a bit here. We can't return a struct. That makes it harder. That's okay. This is okay. This is an okay way of working. We just have a bunch of functions that work with strings in a really unusual and slightly uncomfortable way. The other thing we could do is this, right? Where we subtract from s, right? We subtract from this pointer, and we cast from that, and we say that when we have a string literal, we actually advance by 2. Because if we have a look at this data, right? If we have a look at, apart from the fact there's a compiler error, that's great. Oh yeah, because this thing, like, it doesn't know what this is. It'll probably let me do this. Nope. No struct field reference, s, pointer car. Yeah, okay, that makes sense. I equals 0, I less than sterlen s. We do this, we do it like this, right? So the length is some magic property of the string that is calculated based on some pointer magic. I've seen this done before. And then all we would need to do is when we compile an expression that is a literal string, whatever value we end up pushing here, address, we just have to subtract 2 from it. Oh no, we have to add 2 to it, sorry. Because then when we look at this data, our string points here. This is the data we've pushed into our static section, but we're going to start looking here, right? So we're going to add 2. So rather than looking here, we advance 2 bytes. We look here instead. That might work. What happens if I run this right now? What's it going to do? Bin VM. Let's run our input, and I mean it does something. That's kind of fun. I don't know what it did, but it did something. It didn't crash, which is great. And that's probably because we just returned size of int for some reason. Don't exactly know why, but that's okay. Let's return sterlen tt. Let's see if we can actually get the length of this string. And our string is, in fact, not 28,518 characters long. I wonder if that is... that's probably not the address either. Let's look at what my machine's doing. Let's have a quick look. So let's work backwards and see if we can work out where this garbage value appears. Where does A get polluted? We pop from A. We push from C, so it's whatever's in C. C push load word C. So we're loading from address 4. We're loading from address 4. Why would we be loading from address 4? This global would live at address 0. This string should start at 2, so that's good. Oh, right. Maybe this. Maybe this. Maybe because I forgot to do the thing. And actually, let's just simplify this even more. Let's just dereference this directly. It's because I was doing the wrong thing. A equals 7. Nice. So string length appears to work. That's good news. That's good news. So will print work? Let's try it. Let's print a string. We're not going to return it. There's nothing to return anymore. Okay, this address is out of bounds. And this is good news because it should be out of bounds. We don't have this much memory in our program. I added a cool thing last stream that I should probably call out, and that is a header called a heap header. Or a section called a heap section. This tells the virtual machine where we expect the heap to live and how big we expect it to be. Okay? I think this is a really important thing. This means that we no longer have to guess about where we can use memory. It means that can actually be baked in directly to the virtual machine. Now, there's still a problem in that this is a code assumption, and in this binary, like if I want to get some memory, I have to say, let pointer equal hex 1000 or something. But at some point, I think I will probably add some kind of constant, so I can say heap start. And then we can like malloc and stuff within our program's allocated heap. Maybe there'll be some kind of system call for mapping additional memory into the virtual machine. That might be overkill for such a simple machine, but basically I want to remove guesswork. Things like this, right? When I look at my plan for the stream, which is gone for some reason, here it is. Okay, we're fine. When I look at my plan for the stream, that's what this is going to be if we get to it. Basically, I'm streaming today for as long as I can until I get too hungry to continue. That's my goal. Cool. Please take breaks. I'll take breaks. I've just had a weird late day. I'm gonna do dinner late anyway, so I figure I may as well fill this gap in my life. Nice. So this doesn't exist right now, and this doesn't exist. We've got an I/O output device, like a terminal I/O device that runs in the web browser, but I should add one as well to my actual virtual machine binary. Like, it would be great to map at E1000 with length 1, a new addressable, and it'll be like IO device. Something like this, right? Where when we read and write to it, it's gonna print things to the terminal. And actually, I think we want size 2. We want 2 bytes here. And we're gonna implement this here, I guess. We're gonna make a new struct called IO device. And it's not gonna have anything in it. Impl. We're going to implement addressable for IO device. Cool. So our addressable interface, where is it? Trait addressable. We only need 2 functions here. Oh, 3 functions. We need these 3 functions. One of them we're going to ignore, so that's great. I love when things make my life easy. And you'll notice that when we read, we take a mutable reference to ourself. And that's because, when we have these kind of hardware devices that are mapped into memory addresses, sometimes we might actually want to mutate state on a read. In this case, we don't, but sometimes we might want to. Now, this, we're not going to do anything if we try and zero memory. That doesn't really mean anything. When we read, we're also just going to say 0. But when we write, this is when the real stuff is going to happen, because we're going to println the value that we're trying to write. And yeah, actually no, this is going to be 1 byte. This is going to behave a little bit differently to the one I've written for the web browser because I like to be confusing. Cool. So does this work? No, because I haven't imported addressable. Cool. Memory error not found in the scope. That's because I need to import memory error. Excellent. Things that are unused, that's okay. Address is also unused, that's okay. New not found for the struct, that's also okay. We'll just say default. Oh no, actually we can just say IO device, right? Can I do that? Result that must be used. Okay. Nice. And I might rename this, IO device is okay. IO device is okay. So now what happens when I run this? Translation out of bounds. Because we're writing to E1001. Let's just put like 10 bytes here and see what happens. A equals 7. I don't know why we're getting A equals 7. That's a bit weird. I guess that just is what happens to be in the register at that time, which is fine. Did we get any output at all. It's hard to tell. This is a very noisy output. Oh yeah, oh, okay. This is nice, this is nice. So we're getting numbers written out. And that is literally exactly what I told it to do. That is exactly what I told it to do. Now there's a few things that need to happen here, okay? We're gonna go, so we don't have a current job, bin VM, okay? We need to make this quiet sometimes, only when we want it to be. So let's go into our bin args, and let's add an arg that is quiet. Actually, it should be the opposite, right? Verbose. If we ask it to give us all of this data, then we want it to be loud. Verbose print VM state after every instruction. Otherwise, we're just gonna print out the actual IO that we do. Cool. I really don't need this to be so explicit, but that's okay. I've learnt more about Rust since I wrote this. That's okay. We're gonna say verbose false. Cool. If verbose, if that flag is present, we're gonna say out.verbose is true. I probably should use a library for this. But that's okay. Cool, so now we say if args.verbose. We print this out. Now what happens when we run? Probably gonna compile an error. Yeah, that's okay. Verbose. Where are my args? Oh, this is the assembler. Yeah, okay. Hold on. Okay, my brain broke for a second then. Yeah, we don't even do this. Okay, let's just comment this line out then. Let's just comment a line out. Running. This must be in vm.rs as well. Yeah, well, this can definitely go. We don't want our core library to be printing some garbage out. Okay, so this is nice. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. I don't know why we're printing this much stuff. That's not correct. But we can improve this because, like, what do I want to happen? I want it to print out foo bar. What am I actually doing? I'm just printing out the number value. So I need to reinterpret this value. Can I say value as car? And I want to print, not print ln, because I don't want all these on a new line. I want it to come out one after the other. Nice. Okay, that's really good. Also, I now have output other than just the A register, so that's no longer as important to me. Okay, now this is interesting, right? So why, for any viewers playing along at home, why do I get this output when I'm printing A equals whatever at the end, but when I delete it, why do I get nothing? All right, fun little Linux quirk for you. And the answer, pause the video and think about this, mull this over. The answer, and this is something that will bite you at some point, is that when you have a bunch of stuff buffered on a line, but you haven't ended in a new line, that stuff won't print out. So you have to always end in a new line for whatever you've been building to get actually displayed in the terminal. That's like a really loose rule. There are a million little details for what that can be, but if you want your output to show up, make sure you have a new line at the end of it. Catches everyone at least once. Prof Elements, hello, welcome to the stream. How are you going? Doing any fun coding at the moment? Working on anything cool or interesting? Cool. So, we have a problem. And our problem is, we're doing this thing too many times. We are overrunning our string and then printing out 1, 2, 3, 4, 5 characters worth of garbage at the end. Why is this the case? Because if I return strlen tt, this... Oh, well, we no longer print out what we return. The other thing is, it would be fun to be able to have a putch. So a putch... Can I do this? C car, or maybe I'll just say int C. And then IO out equals C. We'll make it a car. We'll make it a car. We'll see if this works. This might yell at me. Invalid value. Yeah, okay. Now why did that... What happened there? Does this compile okay? That's weird. Implicit null byte padding. Just finished dinner. Implicit null byte padding. Well, so my strings are not null terminated, by the way. That's a fun decision I made because I don't want to deal with that. Expected token. Okay, I forgot a semicolon. Did I? No, I forgot a colon. That's even better. Cool. Okay, now let's run it and see what happens. Putch. Okay, putch may not actually work. Hello? Putch. Can I... That won't work, will it? Will it? Does this work? I think this works. I think I'm allowed to putch a new line. Maybe not. Oops. Okay, that does work. So, Sterlen. Okay, so, hold on. I can turn an integer into a character. What is... So I want to subtract. No, I want to add. I want to subtract. I want... If this is a number like 0, 1, 2, 3, 4, I want to add this to the character 0. Also, what's new line? I should be able to put a new line in. ASCII table. This is the website. This is the one that always comes up. LF, OA, hex A. Let's see what this looks like. Okay, so we put the string length out at the end. So we can actually do this. That's cool. I love when something like that just works. So this is nice. We've got output that looks correct. There's just the case of this garbage. We're overrunning our buffer, and that shouldn't happen. So this is actually code, right? If we look at what gets compiled here, it looks like it's going to overrun the file because this is our string, and then this is the stuff that comes after the string. But actually, in memory, this string comes up like before our executable code. So these are likely these characters, right? And I think if you look at them, oops, can I run the right thing, please? I think Y with an umlaut tends to be FF, which makes sense. If you've done lots of ASCII stuff, you've probably seen that character when you don't want it, which is cool. Okay. I like that we can print new lines. That's really nice. That's really, really nice. And we can print out the string length is correct. Why do we loop too much? Let me just make sure. Sterlen S. Let me just make sure this isn't a weird issue in my while loops. I equals I plus 1. Oops, I have to run the correct thing. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. If this was 14 characters, then you'd be like, okay, it's 2 bytes per thing. But it's 12. So where does 12 come from? How does it ever print out 12 things? S, this is a pointer to a car. This is a pointer to a car. Why is this happening too many times? I think the only answer is to try another string, right? What happens if I say AA equals the string with a single character A? Let's do the same thing again. AA. Okay, what happens in this case? We see the string A and 1, so that's good. We probably want another new line here. It's very silly, but that's okay. unless I want to say, hold on, let me define a better function here. Let me define a better behaved function. Let me define void println. This is good. This is the making of a standard library, okay? All we do in println is call prints and then call putch with the new line character. So now we can say println, and this will put stuff on a new line, which is lovely. Which is lovely. And then I just need a couple of extra putches because otherwise stuff looks weird. Okay. Nice. That's good. I don't need that last one, but that's good. So this string appears to work. What if I add more characters to this string? At what point does it start to break? Okay, once you have 2 characters, it breaks. What about if I have 3 characters? If I have 3 characters, it breaks, but it doesn't seem to add any more characters. What if I have 4 characters? If I have 4 characters, it breaks and it adds another character. Okay, I think I'm seeing a pattern. What if I have 5 characters? I'm expecting to see Y-O-Z at the end. I'm not expecting to see anything additional. Y-O-Z. If I add a 6th character, however, I'm using letters, not numbers, I'm going to see extra data. An extra 2 characters. Okay, so what if I go something like much longer? W, X, Y, Z. And the length is J because we don't have that many. This is like base 26. Or like base ASCII, I guess. Z 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So it doesn't grow. My first thought was, because we added 2 garbage characters when n was 2. Let me build a table of, let me write this, because I think this is an interesting relationship, right? So, n characters and number of garbage, okay? So when n is 1, this is 0. When n was 2, this was 2. When n was 3, this was 2. When n was 4, this was 3. When n was 5, this was 3. Let me go back and just verify this really quickly. A, B, C, D, E. 1, 2, yeah, 3. So what about 6? What was 6? 1, 2, 3, 4, 5. 7 is also going to be 5. G. But then 8 is maybe going to be 7? 1, 2, 3, 4, 5, 6, 7. Yes. Okay, that's really, really good. So now we have a pattern, right? Except for this. 2 is our outlier. Let me just double check the 2 case is correct. Yeah, there's 2. Okay, so for this, it appears that our pattern is... so this is... This appears to be... Hold on. 2 off looks like Sterling being funky. It's not 2 off. It's increasing by 2. Because when it's 26, it was 21. I think this is odd numbers. Well, it increases by 2 for every... Yeah, so it kind of is 2 off. But it's not quite. 3, 3. Oh, no, yeah, you're... So 21... Like, you would expect 26 to go to... You're right about 2 off. You're right about 2 off. You would expect 26. You would expect 27 to go to 25, right? But we know that... So you would expect 26 to also go to 25. But we know that this is actually 21. So let's pick a number in between. Let's say 17, which we would expect to go to 15. But it probably won't. C, D, E, F, G, H, I, J, K, L, M, N. What did I say? 17. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Q. Q the 17th letter of the alphabet. Does that make sense? A. 3, 1, 2, 3, 4, 5, 6. Okay, I don't know my ASCII table well enough. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we're off by 1. So this grows less as it gets bigger. But yeah, Sterlen does feel wrong, doesn't it? The weird thing is, I can print the string length. So, for example, for the 5 case, I can print the string length and I print 5. So, is my while loop incorrect? I've got pretty comprehensive, I can print the string length and we get 5. I've got pretty good testing on my while loop, so I'm not convinced that that's why. Could it be my references? I think I need to load this up in the browser. So let me just rust, oh no. I don't know if I can load it up in the browser, because I'm exporting binaries and I don't know if I, Oh, and VH8T, thank you very much for the follow. Sorry, I missed that one. It snuck by me. I was engrossed in compiler land. Let's look at my VM. Let's println this again, and just dump this into a file called log. And let's just have a look at what's going on. So, where do we get F? Yeah, here. Well, that explains a lot. That explains a lot, in fact. We see that we print FO. What do we print down here? O space. FO, O space. We shouldn't be printing BA. We're printing 2 characters at a time. We're writing 2 characters at a time. I don't know how, but we're writing 2 characters at a time. Oh, found my channel on YouTube quite a while ago. You really enjoy my content. Thank you so much. I always love to hear that. You know, I love the people that have been following along on YouTube. I am making a very meager amount of money on there now, but that's really exciting. You know, I'm going to put that into like getting a tablet so that when I write, it doesn't look like this. I can actually, you know, not use my sick gaming mouse to write text. I can hopefully use a pen. It'll be more natural. Yeah, no, thank you so much. Thank you so much. Welcome distraction from this madness. So let's look at my VM op instruction, try from instruction. I would love to get the instruction. I would love to get the instruction we've just run. Because I suspect I'm storing a word instead of a byte, right? Actually, even better. Let's cut this off right at the source. And I should have known. I should have known this was the case, because when this device is only mapped to one address, what happened, right? What went wrong? What was my hint that this was happening? It blows up at me because it's trying to write E1001. Why is it trying to write E1001 unless it's trying to write two bytes? Okay, so there's a compiler problem. We're writing 2 bytes where only 1 should be written. Let's get rid of this. Let's get rid of this. We don't need it. We know what's going on. So, what's happening? When we're writing to a car pointer, we are somehow writing, and both of these things are car pointers, right? So this is a car pointer. This is a car pointer. We're dereferencing it and assigning to it a car. So we need to work out which one of these things is triggering a store word instead of a store byte. Interesting in making a VM. You're making your own 64-bit in Go. Nice. Cross-reference labels in your assembler. Cross-referencing is hard. Do everything in multiple passes. Just like defer the resolution of symbols until much later. That is my advice. That's what I've done, and it served me well. It makes things a little bit messy to juggle, but I think that's the less smart approach, and it's extremely battle ready. If you're smarter than me, you make passes a better defined thing that you can kind of add to, and you can imagine like a pipeline. My passes are a bit ad hoc right now. It's all a bit loosey-goosey. Dev Ninja, welcome. We are making progress. We just need to work out what part of my code gen. So this is in expression. Code gen expression, and it's going to be somewhere in a deref. No, wait, this is a statement. This is a statement, which I guess is in block. Statement. No, that's not in code gen. It should be in block, shouldn't it? Oh, I was in the wrong file. Okay. Assign deref. Here we go. That's assign array. Assign array gets rewritten as an assign deref. That's fine. Does this possibly rewrite the type? Index? Box new index. Index is the thing. Add right hand side. Left hand side we're adding to the index. Left hand side we're adding it to the index. Does this, so what is the type of a binary operation? Type A, whichever type is bigger. So how does this work? The left hand side is an int. The left hand side's an int. Okay, this is it. This is it. So this is good. This is literally the problem. So when we have an index that gets rewritten, even if we don't have an index that gets rewritten, anytime we say, so even if I rewrite this, because all the compiler does when it sees index s in I, it rewrites this as s plus I, right? It's really, really simple. Really, really simple. And this is actually the, what am I doing? This is the, so this is the left-hand side version. I want the right-hand side version. Array deref, yeah. So we rewrite it, right? What's the type of a binary operation? What's the type of A plus B? It's the type of whichever of those things is bigger. What's the type of I? I is an int. So I can fix this right now by explicitly saying that I is a car. That will fix it. But anytime we have like S5, anytime we have an index directly, that's gonna always mean that the thing we're trying, it's gonna always upcast that to an int pointer, which is not what we want. Very much not what we want. So I need to reevaluate this. If you're adding two pointers together, maybe we want to emphasize the left-hand side. Kuviman, welcome. Am I making C? I'm making C, but with walrus operators, and also compiling to a weird niche 16-bit VM that I'm making up as I go along. So kind of, yeah, I'm making a C-like language. My pointer syntax is a bit different. I don't have weird stars in the middle. But hey, yeah, Kuviman, I've definitely raided your stream before, right? You're doing compiler stuff. Are you the OCaml guy? Okay, so here's what I'm gonna do to band-aid this right now. So I think I can compile and run this now. And something blew up. Okay, so for some reason, if I try and say this is a car, it yells at me. Because why? Assigning from an int to a car. Because you can't assign an int to a car, because every number is an integer. Every number's an integer, but you can't assign an integer to a character without a cast. And I don't do casts yet. Casts are probably the next big thing I need to do. So this doesn't work. This doesn't work. What I really want is to go delve into how this calculation is done. And I think what I want, if these things, if type A and type B, or if type A is a pointer, if type A, let's say matches, I think I do it like this, AST type, and we're still in AST land, AST type pointer? No, wait, I don't want that. If let pointer AST type pointer T is type A. So if type A is a pointer, you're a Rust guy. Excellent. You're making a language in OCaml. The Rust gears are turning. We are rusting, okay? Feel free to leave your Rust tips. Feel free to backseat code. I always welcome it because I'm not a Rust guy. I'm a Go guy. I'm a Go guy pretending to... I'm 3 Go programmers in a trench coat, trying my best to do a Rust. So pointer T, if this type is a pointer, we're always going to say that this type is the type of type A. Always. So if you have like an int pointer A and you say a plus 7, you're always going to say that this is of type int pointer. If you have a car pointer, you're always going to say that a plus 7, it's the type of the thing on the left-hand side. We're always going to prioritize the left-hand side. Rust greater than Go. Go greater than Rust, change your mind. Gopher. Go greater than Rust. Change your mind. Invalid explanation. Go more than Rust, you agree, more pain. Error handling in Go, definitely more pain. I like Go. Go's a really productive language when you have like a bunch of developers working on the same code base. I don't know what it would be like working in a big corporate environment on Rust. I think that would actually be painful, more painful than how like redundant you have to be doing stuff in Go. They're good for different things. I'm sorry for having the uncontroversial opinion, but I think they're good for different things. I really enjoy writing Rust personally. I don't know how much I would enjoy a Rust job. I would give it a go. I would love to learn and see how it scales up to that kind of environment, but I'm not totally sure. Okay, resolve type found AST type. Yes. Why? Because type max. Why? Why is this a thing? Can I just say into? I think I have an into for this, right? No? Expected resolve type. Oh, hold on. I want type pointer. I've already done the conversion. Partially moved. Okay, there we go. Let's run this bad boy. Let's see what happens now. Out of bounds. We're still generating the wrong right. Why should error handling be a pain? Error handling in Go, yeah, you have to do a lot of manual work. There's a lot of copy paste. When something changes, there's a lot of manual work to keep it clean, and it's easy to drop something. There are good linters that will tell you when you've dropped something, but I like the way Rust does it, where it's baked into the type system more. I think it is more clever. Error handling both languages doesn't matter. Rust has results, they're not the main selling points. Yeah, exactly. Rust's standard library and documentation has been phenomenal. It does a lot of really good stuff. Go has Go routines. Go routines are nice. Go routines have a lot of foot guns. But when they're used well and you're doing simple stuff, it's cool. 200 rounds to go. Didn't use Go routines. Yeah. Again, I think the time to reach for Go is if you're looking for a big corporate job. I think that's where it really shines. Rust has more checks at compile time. This is true, but also it depends on the company and it depends on who you're working with. The best thing about collaboration in Go, in my opinion, is that it's a really simple language. Anyone can learn Go in pretty much an afternoon and write good Go code. Rust, you need to be working with good Rust developers so that they can write good Rust code. As someone who's not worked in a professional Rust environment, that's my take. Go is good for newbies. Go is also good for seasoned developers with 15 years of experience who don't know Go. Right? They can drop in, they can learn Go, and they can be productive. Whereas if you want to hire good people, right? You can hire anyone who's a good dev into a Go job, but you can only hire someone who's a good Rust dev into a Rust job. Error handling, don't have to look at. Yeah, I think memory handling in Rust is pretty cool. I think it's pretty cool. Some things in Zig are annoying. One of the people in my Discord, Bobius, who's usually hanging out in this chat, don't know where Bobius is. Sorry, Bobius. It's Zig documentation he was struggling with, right? Some stuff changed, and he wasn't totally sure. Like the state of dependency stuff was a little bit all over the place. Some stuff's changed recently, and it isn't all up to date. You're not targeting newbies. Go devs can continue using Go. Yeah. And there's definitely something to say for it. And if you have like 5 friends and you want to start a Rust company, I think that's great. But I wouldn't sell Rust to like a bank that employs hundreds of programmers. I don't think it's the right fit for that job. And that's more my background. So I would love to try a Rust job and see how it fares in a really like solid environment where you want your code super well tested and you can have like really cool error handling stuff happen at a type level. Probably doing async. I would love a reason to learn async properly in Rust and really just like nerd it out. But I think it puts a lot of demand on having really, really good devs. Like really quality people. And you want quality people anyway, but yeah, I don't know. I think it makes it easier to hire good devs if you're a Go shop. That's definitely been the philosophy of the last two places I've worked that were Go shops. So this builds. Why doesn't this build? So if we're adding two things together and the left-hand side is a pointer, we only care about the type of the left-hand side. We care about the left-hand side. Used Rust results rarely. You don't know why they're considered to be so great. It's the way they interplay with everything. So when you have, I can certainly find an example of this. Let's look for instances of OK or in my compiler. Okay, so anytime you have something with uncertainty, block line 244, block 244, right? Where you have a list of things, or you have a map, you try and get something from the map, and I think this is whatever, you have like a get, and then you get an optional result, like it maybe is present, maybe isn't, then you can OK all that into a result and pump it up the stack. Like that's really cool. That's really cool. Normally you'd want to log the error and continue onwards. I mean, it depends, right? Like option and other monads are great. Results are monad. You're doing monadic operations. You have the power to do that. It's great for that environment where it's like, I want to handle this thing and pass up the chain. I want to wrap this thing and pass up the chain. The way it plays with just returning stuff out, like the way that structure of monad is natively supported makes it really clean to handle errors. And, you know, sometimes you don't just want to log an error. Sometimes you want to return something. .map error is really cool, where you can just map inside the error and do stuff. You never use the new... Yeah, and that's fair. I mean, I think it depends on the way you're writing code. It's perfectly valid to write Go without... to write Rust, sorry, without result. It is definitely valid. Yeah, I mean, if you're handling your errors really locally and not returning from them, then yeah, absolutely. You're not gonna find you use that much. So, why am I still treating this right as an integer pointer right? Because this type should be... I need a better way to inspect this stuff that's going on inside my compiler. I need a better way to inspect it. It's still writing a whole word here. When I look at my expression code gen, okay, when I'm dereferencing an array, left-hand side index, we make a new binary operation. The left-hand side is the left-hand side of the array dereference. The right-hand side is the index. So the first thing we see should be, and let's do the dumbest possible thing here. Let's just put a println. Let's put a println. Let's say found binop. Let's just do the dumb thing. Let's debug print. And this says invalid value because of course it does, because we pipe everything in. Left-hand side has type car. What is going on here? S minus 2, S plus I, that's more interesting than I thought it was. See, I wrongly assumed that when we were adding two things together, well, I mean, I assumed correctly, right? We were upsizing our car to an int because we get the bigger of the two things we're adding. But in this case, what's gone wrong is, for some reason, the left-hand side is actually a pointer to a pointer. Now, what's the size of a pointer? It's 2. It's an entire word. So this is still trying to write a word. So why do we have this double pointer? How are we generating a double pointer here? Why is the left-hand side a pointer to a string? Because that doesn't make sense to me. That doesn't make sense how this has happened. We can very clearly see that I very clearly see how this has happened. I see what's happened. We are in fact very silly, because all this was, that whole time, this function was taking a pointer to a string when it should in fact be taking a string, because a string is a pointer to a car. Beautiful. Okay, we're still writing a word. Is car actually pronounced as car? This is a great question. Is it char? Is it car? I don't know. I've always said car. Car like character, right? It's not character. This is one of these English language things where the letter C is just very silly. Char like chair. Chair. That's like this is the chaotic option. This is yeah. If Eric was nil, yeah. This is what we see in Go. Except often default values are not suitable, right? You have to do something. It's the do something part that can get really messy. Where you have like weird nested error stuff. Everything, Go wants you to line everything up down the left side. You get this triangle of doom. When you do text to speech, it says char, not car. That's good. You're gonna trust a computer over me. I'm a certified warm-blooded man telling you that this is what I hear in my heart. You're gonna trust a machine? I'm gonna add this little silly print back in. I actually think this is kind of useful. This is probably the best way to inspect what's happening at this exact moment. And the left-hand type is pointer to car. So pointer to a car. So what's going on? So the type of this thing is a pointer to a car. It just is. So our deref expression is somehow not treating this correctly. Because we're trying to deref an expression. What's the type of the expression? So what does deref do? What does deref do? Type of. Inner type is type of this expression. Type of this expression should be pointer to car. If it's not a pointer, then we have a problem. It's an invalid deref, so that's good. Compile expression. If inner type. Ah, yes. I see what's happened. I see what's happened again. Okay? Because we're getting the inner type, right? The type of this expression of the thing we're dereferencing. In this case, that will be the type of s plus I, right? Which we know is car. Pointer to car, sorry. The type of s plus I is a pointer to a character. So what's the size of inner type? Is it 1 or is it 2? I said this just before. A pointer is a word, so the size is 2. So what we actually want is the size of the thing being pointed to. If car is based on character, then it would be pronounced care. Character? It's not character either. That's also wrong, unless you're American, which is invalid. Your opinions on pronunciation don't matter because you pronounce everything wrong. So I want to grab the thing inside a pointer, and I know that this thing is a pointer. So let me say, I want the inner type, right? This isn't, I want the inner type. Let's let pointed size equal inner type dot, let's just write a really dumb function. We know this is a pointer. We've asserted it's a pointer. Get, I just wanna get the inside thing. Do I match? Is match the right way to do this? Maybe. Let's say type. It's gonna be a type pointer p, and anything else is gonna panic. So this should not be possible. Okay. Now we want to get pointed size. Excellent. And I forgot a semicolon. This is always the case. Get tie. No LSP. No LSP. I'm not using an LSP. I'm raw dogging Rust. People always have things to say about this. Oops. Match inner type. Okay. LSP is a choice he decided not to choose. Yeah, exactly. I think it's good. I think it's good for exercising my brain and making me think about the standard library. Invalid value. That's because I'm printing garbage out still. Resolve. Get rid of this line. Out of bounds. It's still too big. It's still too big. That's okay. We know that it's right here at least. So this is good. This is good. This is good. So, what next? What next? We have to look at our expression, we have to look at our deref, and we're gonna say... Well, first off, this should be pointed type, not pointed size. So we're gonna do a find and replace without using an LSP. Right? Because that's easy. We're Vim boys. We know how to use :s. Size bytes. I'm just going to println this. Let's see what it says. Pointer type is car. So we should be... Wait, deref. Wait, I'm doing the wrong thing again. This is still correct. I've fixed a bug, but it's not the bug I think I'm fixing. I need to look at my CodeGen block because I'm doing this. This is going on the left-hand side, not the right-hand side. Okay, and it's going to be the same thing. It's going to be the same thing. Type of content right-hand side. Type of right-hand side. What is the type of an assign? Oh golly. Okay, what's the type of this thing? So let's go back to resolve. Type of an expression, a deref expression. Pointer, it's the type of the thing on the right-hand side, right? It's the type of the thing on the right-hand side. The type of a deref expression, the right-hand side, right? So we're dereferencing something on the right-hand side. This is the thing that we're writing. And it's the type of the thing that's being pointed to. So this should be, again, let's just do the really stupid thing and say, let's just println it. Let's just do it. I don't really care. I just want to see some stuff happen. Now. Interesting. These are in fact, even though these get rewritten to be the same thing, they behave differently. Okay? Smartly, I ignore the type of the index. This is good. But here... This code doesn't seem to run. What's going on here? What have I done? I've obviously done something wrong. I'm going to go to the bathroom. I'm going to ponder this in the bathroom and hopefully come back and see exactly what's going on. Because I'm chasing ghosts of the type system right now. I was looking at the wrong thing. I was down here in assign struct field land. I need to be in assign deref land. Okay, so to do a check we can assign, that's still valid. That's still good to do. The problem is that when we write this value, we look at the left-hand side type. Now, what's the left-hand side of this, of any array assignment, right? Any assigned deref, sorry. What's the left-hand side? Okay, let's look at test.code. What's the left-hand side we're assigning to? It's a car pointer. Okay, so this is kind of the same problem we fixed just before. We can't just look at the left-hand side type. Right? That doesn't make any sense. What we need is the type of the thing that the left-hand side points to. LHS type. So we only use this here. We need to, very critically actually, we should say if let some, not some, if type right, so we're gonna do this test. We're gonna move everything inside of here because if this thing's not a pointer, we should in fact not write to it. Otherwise, we're just doing nonsense. You don't want to do that. You don't want to write to things that aren't pointers. That's when your things break. That's when you blue screen of death every Windows computer, like 10,000 Windows computers on a Friday. Otherwise, we're gonna return an error, I guess. I think I have to return, maybe. Do I return something here? Yeah, I think I have to return something here because this is in a loop. We're going to return an error that says compiler error. It's deref invalid type. We have a type for this. Deref invalid type. And that type is going to be LHS type. Excellent, excellent. Cool, so now we have a pointed type, and what we want is for this to be the pointed type, because we're... I think. Let's see. How does right value work again? I think this comes from util, right? Yeah. Here, type. We look at the size of it, yes. Okay, so we're writing the thing that we're pointing to. Nice. I'm also just going to go into resolve and find all those fun printlns that I added, clean them up. Nice. Okay, that's something. That's not what I wanted, but that is something. Why did that blow up like that? What have I done that would make that blow up in that specific way? What are we even doing? Where did this number come from? This is a 66. What? So we're 1, 2, 3, 4, 5. That's too many bytes. Is it? 1, 2. Oh no, sorry. Where? No. What am I doing? But yeah, hold on. 8, 6, 8. This is too many bytes. This is too many bytes. This is 3 bytes. This should only be... What? There's too much data here. We shouldn't be reading and writing to addresses this large. Something very concerning has gone wrong. And that's okay. We're gonna go back, we're gonna add this thing back in. We're gonna try and work out what's going on here. Okay, how much code has executed before we get here? Quite a lot. That's really not what we want to see. Has anything been printed out? Probably not. We're grabbing some addresses here. We have the length of the string, that's good. This is likely the character that we're trying to print. And we probably dereference something somewhere. What did I change? How did I do this? What did I change? I was in expression. I changed a little bit of stuff. What does this say? Dear pointed type. We're pointing to a character. That's good. That's fine. I don't know. We're loading into the C register. We're dereferencing. And this is actually what we're doing, right? We're dereferencing into the C register. Then we push onto the stack. Oops. I'm just going to add my really gross print debugging back in. I also need to go back to expression and get rid of this. Okay, we're going to go back and see what this looks like with our instruction that we're running back in. Store byte. Okay, so we're trying to store something into address C. Pop from the stack. When do we push to the stack? Pop. Why are we popping two things? Because these are our expressions. These are the result of our expressions. That's fine. We're pushing C to the stack. Where does this value come from? 57344. I think we might have actually corrupted our stack. I suspect our stack has been corrupted because I don't see. Let's see if we can find it. 57344. This must have been pushed to the stack at some point, except it hasn't been, so therefore our stack has been corrupted. Has been really messed up, shaken around. Cool. Oof. I might have a little tutoring job lined up. That's exciting. Just sneakily checking my phone in class. Wait, hold on. This value does appear. Here it is. It appears several times. Shift left. Ah, okay. There's only a few places we would ever omit a shift left. Let's see if we can find them. Doesn't happen many places. And it's almost certainly this one. Almost certainly this one. We'll have a look at a few others. 3855 in expression. So let's look at, 38. What's line 38? This is a literal int. Okay, that is possible as well. Except it isn't. It isn't, because none of our literal ints are that big. What did I say? 55 or something? 58? Shift left. This is also part of loading. Yeah, this is the same thing. This is the same thing. Shift left. Cool. Okay. So the other place that this is going to come from is util, this util, shift left. Why would we ever shift left? Because we're trying to load an address that's too big. Now. That's a problem. That's a really big problem. We should never do this. This is bad. We shouldn't be dealing with addresses this large. So why would we ever get here? Why would we ever get here? And in fact, we don't have a failure condition here. We only have a return a vec. So maybe this should be errorable as well. Let's find in expression load address to, is it here? Or is it in code gen block? We only call this two places, assign. It's probably not this. If adder is greater than 1, 2, 3, 4, right? When do we have to do it? Util greater than hex FFF. We shouldn't see an address this big. We shouldn't see an address this big. We're going to return an error, compiler error. I don't know what errors we have. Unknown, invalid index type. You know what? Let's actually just to do it. Address too big. And this is going to blow up my stack and whatever, but that's fine. Oops. What? Adder. My mistake. And that didn't blow up. That's interesting. Where is the other place that we're doing this? In block. Also didn't blow up? So why are we generating a shift left? Cargo R. What am I doing? Bin. Why? Wait, there was another one. There was another one. There was another place that this showed up. Shift left. It showed up in top level, but that shouldn't happen. That shouldn't happen. So do we have a literal integer that's too big? I don't know. I think this is a little too big brain for me right now. I think I'm going to have to think about this more. I'm going to go make dinner. So we'll throw some viewers on to some other amazing streamer. We'll share the love. We'll share it around. We'll share it around. Let's find someone fun to raid. So, I mean, let's quickly check in with my goals. Let's quickly check in with my goals for today while I look at this. Finish strings. Kind of. We're getting close. We're getting close. We didn't get to any of this stuff. This tends to be the thing. I tend to get stuck on the first thing and then not get to the rest of my list, which is a little bit disappointing. A little bit disappointing. But, you know, we're making progress. We're making progress. It is happening. It is happening. There's a Terry A. Davis archive stream. I'm not going to raid someone restreaming Terry A. Davis. Wow. Indie devs. Unreal. Anyone doing compiler at the moment? Any other compiler tags? Tag compiler. Twitch just ate my tag input. Compilers. No compiler devs at the moment. Zero. Nada. Sure, let's do it. Tags don't help, you'd search for a title. Yeah, oops. I struggle with that. Alright, Cricket, taking your recommendation, let's raid this channel, and thank you all very much for tuning in. It's been a fun stream. I will catch you guys next time, and thank you again to everyone who's watching along on YouTube. It's been fun. I'm gonna do with some of the stuff off camera. Hopefully we can get to some of the more exciting stuff again later. Alright, love you all. Bye.